Okay, welcome Palatine Chemistry students. Today we are talking about bond energy changes and chemical reactions. Okay, we're going to do two main aspects of this. We're going to talk about the idea behind it, and then we're going to talk about the math behind it. Because when this boils down to it, it's one big math equation that simply has to do with addition and subtraction. So if you're nervous about this topic, if you can add and you can subtract, you're going to do just fine. Okay, so we're going to walk you through it. If we look at this chemical reaction right here, this chemical reaction is written with its Lewis dot structures here. Okay, these are the corresponding figures. So just a couple things to make note of. You have coefficients. Coefficients indicate how many of those molecules you have, or how many moles of those things you have. And then you can build these. We'll talk about building these structures. CH4 means you have 1, 2, 3, 4 H's and 1 carbon right here. Okay, so we're going to look, kind of just move down, and we'll look at this equation. And what this first talks about is that everything on the left-hand side, okay, these are considered the reactants. The reactants, in order to break, anytime we have a reaction, we're breaking bonds and making bonds. And we have to break these bonds first. Okay, a stick is not going to break itself. A match is not going to light itself. In order to break a stick or light a match, you have to put energy into those things. So this word talks about everything over on this side of the reaction, and this is going to come into play in a little bit. This is all going to be positive. Okay, I have to add energy to that in order to get that reaction to happen. Okay, now how much energy? Well, we got these handy dandy tables right here. These tables are extremely important, okay? You will have access to these. This is nothing you have to memorize, but you do know how to use, need to know how to use these tables. And let's be very clear. There are 3 tables here. There is one table for single bond energies. There's another table for double bond energies. And there's a third table for triple bond energies. That is extremely important, okay? So there is a difference. If I had a bond, let's say I have a carbon-carbon bond. Well, that puts me at 83, okay, kilocalories per mole. If I have 2 of those, well, 83 times 83, okay, or I'm sorry, 83 plus 83. If I had 2 of those bonds, sorry, let me fix my math here, plus 83 equals 166 kilocalories per mole. Well, if I have a carbon-carbon double bond, notice these numbers are not the same. A carbon-carbon triple bond, okay, 83 plus 83 plus 83 would be 249. Well, the point is a double bond is different than 2 single bonds added together. Okay, that's a very important note. It's very important to realize that these tables, there are 3 tables here, and these 3 tables represent single, double, and triple bonds. Okay, so this will be a reference table that we keep coming back to. It's very important that you have access to this and you know how to use it. This is nothing magical. We're going to be looking off this table, looking at the bonds we have, and start building our charges from there. So if I look at this first structure, and this is the structure we started talking about today, this is CH4. Okay, all I have to do initially, I have to look at, to make it nice and bright, I look at each one of these bonds. Here, 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 and here. Each one of those bonds on this structure is a carbon to hydrogen bond. So, and I actually, you know what I did? I have this, and I can put this on the left so we can do two things at once. This would be a very useful thing for you to also do. So now some people get confused. They look at this and say hydrogen, carbon. Oh, it's got an X in it. All that means is that this table's kind of doubled, just repeats itself. So you just have to instead zoom out, and you would look at, not that far, hydrogen to carbon, same deal, okay, and that gives me 99. So if you run into an X, just flip it and look at the other one. X is not an answer on any of these. There is a number value for each partnership. So that's where I get the number 99 from, 99 kilocalories per mole. And you'll notice that each one of those is listed at 99. Okay, so step one is simply finding the bonds, looking at the table, and then going ahead and just adding those up. Okay, so 99 times 4 is 396. Okay. Now I can flip over, and again, this equation, if I pull back, I'm looking at this right here. Okay, this is where I'm getting this from. So we're sticking with that same equation we started the day. Okay, so now I head down here. I look at this bond. Okay, so that is a double bond. That is an oxygen to oxygen double bond. So I would look at my table. Since I'm looking at a double bond, I look at my double bond energies. I have oxygen to oxygen, 118. So I have 118 and 118. That gives me a total of 236. Okay? So all of this added together is 632 kilocalories of energy needed to break that bond. Okay? Or I should say those bonds. Okay, so you have all those bonds in there. In order to break them, you need 632 kilocalories of energy. Okay, you need to add that much. And that's why if I look at this chart right here, here's my energy. And I see that this goes up because I have to add that to the reaction. So I have to put energy in to break that stick. I have to put energy in to light that match. So my energy is going to go up in that reaction. Okay. If I look at the other side, okay, here's the other side of that reaction. So now I'll do this without doing the cheat sheet. So I'm looking at this bond here and this bond here. So this happens to be an O double bonded to a C, O double bonded to a C. I will look at my list. And here, 185. It doesn't matter, by the way, which order they're in, O to C, C to O. These molecules are moving in space anyway. Oh, I forgot what my number was. What am I looking at here? 185. Okay, so these are each 185, 185, 185. Okay, and those total up right here, we'll see, to 370. And then I do the same thing to these two water molecules, okay? And I have 111, 111, 111, 111 totals to 444. So then here's my reaction. Totals 814. So let me back up. All we're doing, we have these structures. We go through each bond and we make sure we know what each one of these bonds is worth. And then I simply add those numbers together. So, as I discussed right off the bat, if you can add and subtract, you'll be fine at this. You have your table of bond energies, you find the bond, you add them together, and you get it. So, now this, when I have that reaction, I notice that energy is released. So I see an inverse graph, an indirect relationship here, in which the energy goes down. Okay, once I light that match, it loses a lot of energy, becomes an exothermic reaction, and gives off energy. And that total reaction coordinate is going to drop. Okay, it's going to decrease. Okay. Now, what I want to do is look at this main equation. Looks fancy. It's not. Okay, it's not fancy. This is simply saying reactants, products. Okay, so this says my total energy equals the sum of my reactants. This is the sign for sum, so you add them all up. The sum of the reactants plus the negative sum of the products. Or to make it even easier, in which this is the one we are going to use down here. This is the verbiage I will use. It's the same thing mathematically. This is like the purest form to use this way, but this is what I'm going to use. Continuing on in this lecture, I'm simply going to say the total bond energy is equal to the sum of the reactants minus the sum of the products. Add up the reactants, subtract the products, there's your total energy. That's it. Okay? So let's look at some of these examples. We'll walk through these, and hopefully that should clarify some stuff. So if I look at example 1, okay, first step, I have to get my bond energy chart. There's no way to do this without the bond energies. Okay, I see students look at these and they try to magically come up with an answer. You need to look at the bond energies. So I first have to find hydrogen to hydrogen, okay, 104. And then this one just happens to be on my screen, so we'll say fluorine to fluorine, 37. And then we'll come over here and we'll say, okay, H, let me clear this off. HF 135, 135. Okay. All I did, I looked on the chart, I got all my numbers, that's it. Now, I'm going to simply add these together. So 104 plus 37 is going to give me 141. Okay. And then over here, 135 plus 135 is 270. That's it. And now, all I would say is 141 minus 270, and I get negative 129. And that is my total bond energy for that reaction, negative 129 kilocalories. All right, let's take a look at example 2. We're going to go through the same process. We are going to start by looking at this structure. I'll get my bond energy chart. And again, this is no secret. We're going to look at the bond energies, list out all the bond energies. Once we list out the bond energies, we add them all together, and then we subtract the two sides. That's it. Okay. So the only trick here, this bond in the center, a lot of people will use this incorrectly. We'll use 83 twice. That's not correct. It is a double bond, so you need to use the double bond energy chart. So it's 147. So this bond here is 147. And then all the others are hydrogens to, hydrogens to carbons. So all those are going to be 99. Okay, so if I was to kind of list them out, I would say, I can say 147 plus 99 times 4. However you want to set up your math, that's fine. You do it any way you want. I'll get my calculator out in a little bit here. Right now, I'm just going to keep listing these out. I have to find a chlorine, which is going to be right, I find where they intersect right here. So 58, okay, and so now I can add these guys together. If I was to look at, I've got my calculator here, 99 times 4 is 396 plus 147, 543 plus 58. Gives me a total on this side, and this is what I kind of like to do. I just make my numbers very large. and a distinct color, and I say this whole side is 601. All I did, I found the bonds, I added them all up, I now have a total for that side. I can go through that process on this side. I'm going to find all these bonds again. These are all 99s. And again, different way to do it. If you want to write on each bond, be my guest. 83. And I'm just looking over here, okay, what we've been doing this whole time. Here's 83. Okay. And chlorine to carbon is, let's see, we got carbon here, chlorine here. So I find where they intersect. That will be 81. So these are 81, 81. So if I add all of those up, I'll put it on here. I have 99 times 4 plus 83 plus 81 plus 81. I add them all up, and I have 641. So again, you can just simply, in a nice large font that can't miss, 641. 600 minus 641 gives us negative 40. So that is the answer to this problem. Again, this looks intimidating. You have these very large structures. You know, if I was to erase all this again, I look at all these big structures. It looks intimidating, but at the end of the day, you use your chart. You simply find your charges, your bond energies, and you add them up. You get a total, and you subtract the two sides. That's it. Big minus sign in the middle. Okay? Hopefully that helps.